All right, welcome back, folks. It's my great pleasure to welcome Claus Kiefer from the University of Cologne for our first speaker this afternoon. So, yes, please take it away.
Okay, thank you. I, of course, thank Christian and the other organizers for inviting me here again to Geneva. So it's always a pleasure to be here. And my talk is about decoherence of Schrödinger's cosmic cat. You've already heard about both the cat and the decoherence in the morning, and I will focus more now on decoherence of quantum cosmology. But before doing that, I somehow review briefly decoherence in quantum mechanics, where it all came from, because in quantum cosmology we learned from what we did in quantum mechanics, and we just take those results. Then I have to say something about quantum gravity, because quantum cosmology is based on a theory of quantum gravity, so I have to be explicit there what I use, and then the main part I discuss decoherence in quantum cosmology, both for all of space-time, but mainly for the primordial fluctuations that were briefly mentioned in David's talk in the morning. So here there will be more explicit calculations on that, how the quantum to classical transition proceeds for the primordial fluctuations. And I end with some reflections, and this is maybe also the transition to the discussion and to the dispute. Now here we are in Geneva, and of course Genius Loci, John Bell was here for many years, and so I should maybe start with a quote from him. I should also say that I attended 2 talks by John Bell in the 80s, and I remember in particular the one of 87 in Vienna, when it was 100 years of Schrödinger's birthday. And because he's very fond of cats, Bell, in that talk, he modified the cat experiment, and not killing the cat, but having a mechanism so that if the 8-atom decays, then the cat gets milk and is filled, and if the atom does not decay, it does no milk, so he wrote down. At that time we had, of course, overhead transparencies, a filled and an empty cat, on which he based his talk. But of course, Schrödinger, with dead and alive cat, this is much more drastic to pose the problem, because dead and alive is much more pronounced than just having filled or not. Here, this quote is from paper Quantum Mechanics for Cosmologists, already from 1981, and he wrote there, when the system in question is the whole world, where is the measurer to be found? I guess this is one of the questions that we are discussing here. Inside rather than outside, presumably. What exactly qualifies some subsystems to play this role? If the theory is to apply to anything but idealize the probability operations, are we not obliged to admit that more or less measurement-like processes are going on more or less all the time, more or less everywhere? That's also what I interpret, of course, to make a point for decoherence, although in that year John Bell was not discussing anything like quantum to classical transition. In that year he was mainly entertaining the Breuil-Bohm approach. In that talk in Vienna of 87, which I remember, he was more than addressing this then new GRW approach of collapsing the wave function. But since he died in 1990, it's not sure what he would then maybe said later about the future developments. Now, the main issue, of course, in quantum mechanics, at least as I see it, and you find it also the first sentence in Dirac's famous textbook, is the superposition principle. And so I formulated in that form, let psi1 and psi2 be physical states, then alpha psi1 plus beta psi2 is again a physical state with alpha and beta arbitrary complex numbers. For more than one degree of freedom, this leads to the entanglement between systems, or Verschränkung in German, as Schrödinger originally called it. Linearity of the Schrödinger equation then is the second thing. So the first thing is already a kinematic. I, by purpose, divided up the superposition principle into the pure kinematic part without having a dynamical equation yet, and then the dynamical equation. And of course, the dynamics is in accordance with this principle, so this is the linearity of the Schrödinger equation. The sum of two solutions is again a solution. Here we talk about solutions. So classical states form only a tiny subset in the space of all possible states, because you can superpose me standing here and there, and you have the cat with milk and the cat without milk. As Schrödinger put it in 1935, I would not call that one, but rather the characteristic trait of quantum mechanics, the one that enforces its entire departure from classical lines of thought. By the interaction, the two representatives of psi functions have become entangled. Another way of expressing the peculiar situation is the best possible knowledge of a whole does not necessarily include the best possible knowledge of all its parts, even though they may be entirely separated. I mean, separated in pure space, like in the EPR situation. The experimental tests of this principle are abundant, and you learn about that in any course, and this is maybe an incomplete list. But because it's so important, I have put some examples. So the binding energies of atoms and molecules. So very early on, I think it was Relevance in Norway around 1930, who already pointed out that you cannot understand the binding energy of helium atoms without entanglement. I mean, the word was not coined at the time. Because the electrons, which are two in the helium atom, they are entangled, and if they were product states, you would get wrong energies. So already at that early days, it was before EPR and everything, it was founded. Then the interferences of fullerenes and more complicated molecules, say in the Vienna experiments, the switch paths or Welcher-Weg experiments, entanglement of atomic states with atomic momentum. There's also more recently, in the context of this quantum information developments, entanglement of photon pairs over distances of more than 100 kilometers, or even this Mitzius satellite by the Chinese. It's more than 1,000 kilometers, at least according to this paper. Superposition of macroscopically different currents in squids. And of course, it's not restricted to non-relativistic quantum mechanics. I mean, the superposition principle abounds also in particle physics, like with the neutrino oscillations and the KK bar oscillations and all that. So this is a well-established principle, and we have not seen any violation so far, except maybe what is related to the measurement process discussion. There is one example that you most likely know in Vienna, already 20 years old. There are these molecules, and these are biomolecules, you find them in the blood. Yeah. I don't pronounce it now maybe, but these are very heavy molecules, and you can check the interference pattern of that porphyrin. Yeah. And I don't know, more than 1,000 atomic units or so, and the superposition principle is fine. Now the measurement problem you have already encountered in the morning, and I don't want to bore you too much with repeating things. Maybe just briefly, you have this coupling between system and apparatus, and you want to measure by the apparatus a certain property of the system. And so if maybe a spin, so you have maybe spin 1/2, so possibilities of spin up in a certain direction and spin down. Here it's generally called n. So n you can just imagine maybe up and down. And find notice the initial switched off state of the apparatus. And then there is some interaction. Okay, measurement takes place by an interaction, of course. And then measurement should be, at least in an ideal case, so-called ideal measurement, that the system property is preserved. So say if you have spin up, then you should measure spin up, and the state of the apparatus shows that it's spin up. So phi n of t means, maybe in the old-fashioned discussion one uses pointers and the like, so maybe to the right then it's spin up, and to the left is spin down. And so this is the phi n. So far so good, but you can also suppose spin up and spin down, and here, for example, spin right, or for you it's spin left. And then you can superpose these ends. And so this is the second formula. And by the superposition principle, you now end up not in a definite result showing spin left, but in this apparently weird superposition that includes not only the spin, but also the apparatus. This is why we call it a measurement problem, because if it were only something in the microscopic world, then we would not be bothered very much, but it translates to the macroscopic. And of course, Schrödinger's cat is just an example of that. This is a macroscopic superposition. And John von Neumann, therefore, in 1932, in his famous textbook, introduced this collapse of the wave function as a new dynamics in addition to the dynamics given by the Schrödinger equation. He even called it erster Eingriff, first invention, and the Schrödinger equation second, so it even for him has the prime status. But of course, he was not explicit there when it really happened, just in the measurement. Now a big jump, and I'm very brief here. So one key to understand this, and it's certainly not enough to understand the final issue, otherwise we were not here, is the inclusion of the environment, which C in Heidelberg for the first time did in 1970. So he noticed that in fact any macroscopic body and an apparatus is a macroscopic object, is not isolated. Yeah? It's coupled to what he called the environment, Umgebung, the environment that typically is maybe photons coming and scattering off, or air molecules coming and scattering off. And so that paper of 1970 gave explicit numbers of how bad the assumption of isolation would be. And so we have to take into account not only the apparatus, but also the environment, which is then here done in the first formula, and it's maybe more or less a repetition of the previous slide, just that you have now not only system and apparatus, but the initial state of the environment, and then as time goes on, and there are many explicit examples that C and Zurek and Joos and others discussed later, that this gives them a gigantic superposition, including the environment. And so at first glance you would say, well, this makes the problem worse, because you not only have here my apparatus here, but you also have the whole environment. But now comes the key observation that C introduced, that actually all local observations, these are the ones only of system and apparatus, but not the environment. They follow from the reduced density matrix of system plus apparatus. And in general, and explicit calculations confirm that in general you have that different environmental states are roughly orthogonal to each other, just because, I mean, if you have here, I mean, explicit example by Joos and C is a dust grain, where you measure that is in superposition at different places, and so if a photon comes and scattered off, then of course the photon scatters locally, and it takes away information about the position of the scattering that it takes place, right? And so whether it's here or here, so these are then approximately orthogonal states of the photon. You know? And so this is a realistic assumption of what happens in this apparatus situation. Of course, in experimental situations like the Vienna experiments, you really take a lot of care to switch off this, you know, but really have to take care. So in ordinary situation, the environment is there. And then you get this here, which looks like a classical stochastic ensemble. You know? So with these probabilities Cn squared that come from here, and with both the system and the environment is there. So you could say, yeah, the interferences exist, but they are not there. I mean, they exist in the gigantic system of system, apparatus, and environment, but they are not there whether you look in your lab. So you don't see them because they're going away. And this also applies to Schrödinger's cat and so on. And this gave then rise to decoherence, which I mean here decoherence by the environment. I know that is sometimes used in other contexts, but in the context that C and his followers then used its decoherence by the environment, and I define it in this way: irreversible emergence of classical properties through the unavoidable, and I should also add maybe irreversible interaction with the environment. And objects then appear classically, although they are fundamentally described by quantum theory. And so I've learned in what we have seen in the morning, of course, fundamentally we don't have probabilities, we have amplitudes. And by this process, objects that are fundamentally interfere and maybe not classical, they appear classical. And this appearance can be tested experimentally. I will show you an example. Okay, these are some early papers. So before the first experimental tests were made in 1996 by Serge Arroche in Paris and Vineland in Boulder in the US. Not so many people worked on it, and it was met a little bit with suspicion also, this kind, and only after the experiments are there, a broader community of physicists was convinced. So that's, and here, I mean, there are now many examples, and for example, Max Schlosshauer has written a detailed review on what all the many experiments that you have for decoherence with grids and with other things. So you may consult this review if you like to see experimental details. This is from the Vienna group, and the left is, I mentioned this briefly as a comment in the morning, the decoherence through particle collisions on the left and through heating of fullerenes on the right. And these curves that are, okay, this is over time, so you increase pressure, and then the visibility of the interferences goes down. This is what decoherence means. So what usually happens in everyday situations very abruptly and looks like a jump in these very carefully constructed experiments, you can really see the time evolution. And it's not a jump, it's something that occurs continuously in time. And these curves, these are not fixed apparently, but these are theoretical predictions. For example, especially the one by Jos and Zeh, who in '85 for the first time really calculated realistic situations of decoherence. I mean, not just oscillators interacting, but I mean real atomic physics like Thomson scattering and the like. And I may add by this, I mean, Jos and Zeh was '85, so this was 20 years later, so they even discovered experimentally a trivial mistake that was done in the calculation, a 2 pi was missing in that result. So instead of delta function, it should have 2 pi times delta function. They noticed in the experiment result that there is apparently a factor of 6, of the theoretical prediction, yeah, which is the 2 pi. So you saw that really in the experiments. And of course, then you could correct, yeah, you must be careful when making a square with delta function, and the 2 pi should be there, okay. So you see how close, I mean, now from the early days of maybe your theory, that you really can do concrete experiments and even discover a theoretical mistake by experiment. So we should all be careful when doing theoretical calculations, because in 20 years, some clever laser physicists come and they find by experiments the mistakes. Of course, another thing now is the interpretation, and we already had this in the morning. So what are the options? This is, of course, what my personal opinion, but I think it's beyond that. The superposition principle and the Schrödinger equation are universally valid. And this leads to what is called, and what we already had in the morning, the many worlds or relative state or average interpretation. So the dead and the alive Schrödinger-cat indeed exist simultaneously in different branches, so you have no probabilities at a fundamental level, just the amplitude. That's all. So I will entertain this idea in the following, also when I do the quantum cosmology. We will have some alternatives here. So I mentioned both the second and the third part, so that current formulas of quantum theory must be modified in order to accommodate a collapse of the wave function, such that only the dead or the live cat exists. I guess that David will talk about maybe in the cosmological context about this. And that there also may be a change of the kinematical structure, so the Bohm theory, and I guess that Ward will tell about that. So this is I will not include that, but I will entertain the first part only. There may be pure epistemic interpretations, which one could say a lot, and I recommend you to read the essays by John Bell in his Unspeakable, where he's very critical about this. For example, he calls the complementarity of Bohr a romantic interpretation, and so on. I mean, for him, only words, and so on. So these are the options I think you have, and I will focus on the first. So what about gravity? So far this was just quantum theory, and this is a classic gravitational field. Do we need to quantize gravity, and if yes, what consequences does it have? Now this is not yet a finished subject, but historically I like to point out to this remark by Richard Feynman at an important conference in North Carolina, 1957, when he considered this Stern-Gallasch experiment, the usual one. You have an inhomogeneous magnetic field, and you have the electrons or maybe silver atoms that it's spin up. It has been up, goes to counter 1, spin down to counter 2, and if it's spin to the left, then it's a superposition. And he imagines that this is coupled to a ball of macroscopic size, and that is superposition. Well, it's also like with the Schrödinger-cat, translates from the microscopic to the ball in a superposition, but the ball has a measurable gravitational field. For example, by Cavendish balance, you can measure it. And okay, to quote him, literally, if you believe in quantum mechanics up to any level, then you have to believe in gravitational quantization in order to describe this experiment. Yeah, because then you have, if the ball is in a superposition, you can measure the field. What does it mean for the field? I should also have a superposition of the gravitational field then, if the ball is at the same time here and here. It may turn out, since we have never done experiment at this level, that it's not possible. That there's something the matter without quantum mechanics when you have too much action in the system or too much mass or something. But that is the only way I can see which would keep you from the necessity of quantizing the gravitational field. It's a way that I don't want to propose. And in fact, all the concrete, or the overwhelming majority of concrete approaches to quantum gravity preserves the linearity of quantum theory, so the linearity of the quantum state. So even string theory, which is very complicated, you go to 11 dimensions, you have Calabi-Yau manifolds, and so on. But when you look in the books, you have A's and A daggers and oscillators and the standard superposition principle. So all these approaches preserve the linearity, and therefore have, of course, the superposition of even macroscopic gravitational fields. And the only option is, of course, to have a theory with an explicit collapse, for example, like Roger Penrose and Lajos Diósi suggest, but compared, say, to string theory or canonical gravity, it is not that much developed. There have been in recent years speculations about observing gravitational superpositions in the lab, so-called graph-cat states, and I think earlier references were the ones cited here, that two test masses are put in spatial superpositions. They can become entangled with each other if, and only if, it's claimed the mediator, the gravitational field, is quantum, and that if you can demonstrate that it's a proof of quantum gravity. Now I'm very suspicious of that, and but I don't want anyway. It's not the subject of my talk today, so I will only mention this. It would be maybe for a separate meeting about whether quantum gravity in the lab is really testable or not. But I still want to have a footnote on that here. Now, but now turn to quantum gravity. John Wheeler once wrote, "No question about quantum gravity is more difficult than the question, what is the question?" And sometimes in conferences, still you have the feeling that this is what we discuss, but also what is the correct approach. Yeah? I mean, if you talk about quantum gravity, maybe person 1 has a different thing in the mind than person 2. Now, the general well, the main developments that you find in the literature, or when you go in the morning to the archive, is that quantum general relativity is one. So you start with an established classical theory, and this is Einstein's theory of general relativity. Sometimes you use also some classical modifications, f of r series and the like, but let me here quantum general relativity, and you apply then heuristic quantization rules, like we did earlier, say for quantum electrodynamics, say. And then you arrive at a theory called quantum general relativity, and depending on the methods used, you arrive at different formalisms, mainly the covariant and the canonical approaches. The covariant approaches are approaches where at each step in the formalism you have some four-dimensional quantities, and typically today this is the path integral. I think we have seen the path integral in the morning already, but this is where you integrate over all metrics, space-time metrics. The canonical approaches are the ones where you try to find the Hamiltonian and try to devise a Schrödinger type equation with wave functions or wave functionals here. And the oldest method, going back to Rosenfeld of 1930, is quantum geometrodynamics, so that you quantize the metric variables. It actually turns out, as you will see, the three-dimensional metric and its momentum. More recently, of course, you have also the option to use other variables, like the connection variables very close to Young-Mills theory and the loop variables leading to loop quantum gravity. Then string theory is of a very different type, because string theory does not quantize classical relativity. It also quantizes something classical, but it's not classical relativity. Classical relativity is recovered in a certain approximation. And so it starts with a quantum theory of all interactions ideally unified, and then quantum gravity only comes in a certain limit. And there are also other approaches, fundamental discrete approaches such as quantum topology, causal sets, group field theories. Partially they've grown out of the other approaches, partially they have been devised on their own. So I have to make a choice, of course, and for two reasons I choose the quantum geometric dynamics for the following. First, of course, because I have maybe most experience with that over the years, and second, because this is still one of the most conservative approaches. And so using just the metric variables as Einstein used them. But this does not mean that you cannot discuss issues I discuss in the following, that you cannot discuss them in these other approaches. Okay, quantum geometrodynamics, I mentioned Rosenfeld, so there were other people like Dirac, but I think in clear words, maybe the first who wrote the equations down and also discussed their physical meaning were John Wheeler and Bryce DeWitt in 1967 and 68. And the result is, okay, it looks complicated here. So if you don't know it already, then maybe you don't have to have a careful look. But what is important is you find here constrained equations. So you don't get any external time, t, anymore, but you get, instead of, say, a Schrödinger equation, you get the equations of the time h of psi is 0. And this is split up into 1 h orthogonal and 3 ha, but this is due to the formalism and because we have four-dimensional space-time. But the essential message is you have equations h psi equals 0, and this holds equally for, say, loop quantum gravity, because also loop quantum gravity is a canonical quantization of general relativity just with different variables. And the explicit form looks different. We have seen a difference equation in the morning as an example in cosmology with different variables, but in quantum geometric dynamics it looks that. And the only, we have wave functionals, and from the gravity side only the three-dimensional metric enters, not the four-dimensional. So why that? Of course, you can go through the formalism that was discussed long ago by Arnold, Gies, and Miesner, but you can also follow, of course, John Wheeler's more physical arguments that you find, for example, nicely explained in the thick book Miesner, Thorne, and Wheeler on the later pages. If you went so far, then you find a nice discussion. And you see here on the blackboard, it has the classical mechanics for one particle. So there's a trajectory, to come from A to B. But if you quantize, then the trajectory is gone. You may attribute it to the uncertainty principle or to the general quantum mechanics. You just have a psi that depends, say, in the space representation on the position. Of course, in addition, you have in mechanics the external time, because the T is Newton's absolute time. But when you apply the very same formalism to Einstein's theory, there is no time outside space-time. So only have the space-time, and space-time corresponds to the left, like a generalized trajectory of spaces, three geometries. And if you apply the very same conservative formalism, identifying the P's and the Q's and having a non-trivial commutation relation between P and Q, then the space-time is gone in the same way as the trajectory is gone, and you only have the three geometry. So that's a straightforward consequence of a conservative attitude of quantization. Okay, but my talk is about quantum cosmology, so although at a general level there are very nice things to discuss, like concept of time and so on, I focus here on the topic of the conference here. Now, quantum cosmology is the application of quantum theory to the universe as a whole, and so everything is intrinsic to the universe. There's no external observer here outside the universe. So Gell-Mann and Hartle said it as follows: quantum mechanics is best and most fundamentally understood in the framework of quantum cosmology. So because they thought that even in standard quantum theory, it's best to have a formalism, an intrinsic formalism for quantum theory, not the one of Bohr where you have by definition a classical observer outside, but you should understand the emergence of classical properties intrinsically from a quantum formalism, using amplitudes and a fundamental way. Again, John Bell, one of his last essays, he died in 1990, a serious formulation of quantum theory will not exclude the big world outside the laboratory. So in the same way, although I think the minority has not contacted with Gell-Mann and Hartle at the same time, the same year, but it was the same idea. So a universally valid quantum theory, and I will assume that it's universally valid with the average interpretation, must be applied to the universe as a whole as the only closed quantum system in the strict sense. So that's a step before you really do quantum gravity, but if you then take the universe as a whole, you see that gravity is the dominant interaction on cosmic scale. So if you really want to do concrete investigations, you have to do quantum cosmology based on quantum gravity. And I use the Wheeler-DeWitt equation and canonical quantum geometrodynamics. Yeah, this is just an old example of mine, not yet related to decoherence, that you can do with the Wheeler-DeWitt equation, things you can also do with Schrödinger equations like constructing wave packet. So a simple example of the Wheeler-DeWitt equation, h psi equals 0, is the one where you couple a Friedmann universe with scale factor A to a conformally coupled scalar field here denoted by chi and an appropriate choice of units. And classically you find these are shoe ellipses, and if you do quantum calculations with appropriate initial conditions, you can construct wave packets, for example. Now an important thing, and I think that's also important for our discussion here and for the discussion in the morning, whether space-time is a prerequisite for the measurement problem or vice versa, or is independent, is of course how you can recover, at least approximately, a concept of time and space-time from a timeless formalism of quantum gravity. Now this has discussed for some while, starting with the pioneering papers by DeWitt and Wheeler, and in particular then by Lapczynski and Obakov in 1979 already, that you can do this with a Born-Oppenheimer type of approximation. Now Born-Oppenheimer, this is something old, and this is a kind of daily bread for molecular chemists, because they cannot solve Schrödinger equation for complicated systems, and so they either do a numerics or they do approximations, and Born-Oppenheimer is often very useful because it separates the nuclei from the electrons through their mass scales, because nuclei are, the proton is 2,000 times the mass of the electron, and so you can make a scheme where you make use of that separation of scales. And you can make a similar things also in quantum cosmology. Okay, the details maybe would take me too far away, but the point is here, and here the example is by Halliwell and Hawking of 1985, that you have the background, the Friedmann background, and only small perturbations, like we observe in our universe, that we have approximately a Friedmann universe. And these perturbations are labeled by xn formally. The n can maybe several indices and so on. And the h psi equals 0, then the psi depends on the background. So alpha is the logarithm of the scale factor, just for convenience, and a scalar field like the inflaton field and the multipoles. And then if we make an ansatz, like the one with the capital psi is psi naught times the product over all psi n, and if the psi naught is of this WKP form, we can, after some calculations, recover this equation. So suddenly there's a t there. There was no t in the fundamental equation, but the t has emerged in that approximation process under certain conditions, and it's just a substitute for, this is in the phase of that background wave function, and this nabla refers to derivatives with respect to alpha and phi. So this is a directional derivative. So in this, this formalism, it maybe doesn't look familiar when you first see it, but it's not so far from the recovery of geometric optics from wave optics. It's called the Iconal equations. So in wave optics, which is more fundamentally of the wave, and in geometric optics you have light rays with lenses, and the light rays are approximate concept. And the formalism is very similar, even if this is a very different situation. So you have fundamentally these wave functions, but under certain conditions you have the light rays would be the space-time. So space-time is emergent here under certain conditions from the timeless full equation. And then, of course, the question arises if what happens then with the classicality. We observe a classical universe, apparently, but if we have quantum gravity and we can superpose different three geometries, how and to what extent can we say that a classical universe emerges? So in quantum cosmology, you can also have arbitrary superposition if you believe in the linearity of the theory. That's of course an assumption that may be wrong, but if you believe that, so how can you understand the emergence of an approximate classical universe? That's what C actually posed as a question to me as the supervisor of my PhD thesis. So that was then in '87 that I published this result, that you have then decoherence. And here's only one example. I have no time to go through these calculations. And it was also mentioned briefly in the morning. I mean, decoherence by the environment you shouldn't take literally. These are irrelevant degrees of freedom in configuration space that are not accessible. So not in 3 space, but in configuration space. And here we used, or I used that formalism of Halliwell and Hawking, where you have this big configuration space with the background, A and phi, and then all these multipoles. And these multipoles, they can be, for example, weak gravitational waves like gravitons, or they can be small density fluctuations that later grew into the what you see in the CMB anisotropies. So these were considered then by us as the environment. And then you can show how and to which extent the A and the phi become classical, which I have not here on the transparencies, but which one can technically discuss. What I have here is another example, namely, you could, for example, and this was also a point that was in the early years criticized, that we and others use this complex solution to the real equation. I mean, the Wheeler-DeWitt equation is real. There's no I, no imaginary unit in it, in contrast to the Schrödinger equation. So why should we use that? So why not do, say, a superposition of the two with the e to the minus I, which is a cosine, say. Karl Kufasch often made this critical point to me in early years. And so the question, then the calculation shows that actually these two components decohere. And it's very similar to what we have in molecular physics, namely if you have, say, chiral molecules like sugar. So the solutions of Schrödinger equations, they are parity invariant. But, I mean, these sugar molecules say they have a certain chirality, left or right. So how come? No? And this was long considered a paradox, Hund's paradox from 1927, but decoherence in quantum mechanics has explained that the structure of these molecules emerges if the molecule is big enough. So if you, for example, go to the molecule NH3, the effect is not big enough. So ammonia is too small to be decohered, so it is in a superposition, and this is the ammonia maser that you observe in cosmic distances. But if you already substitute the NH3 by PH3 with phosphor, which is next line in the periodic system, then it's so strong that it does no longer give you superpositions. So decoherence actually explains quantitatively, not just by words, when and to what extent these things become classical. And for example, I did in that early calculations here applied it to quantum cosmology with the gravitons as the environment, and found one example of today's universe, this very small number giving the interference term. So the present universe or big enough universe then turns out to be, I mean, classical to extreme accuracy. This is why classical cosmologists are very successful, in spite of the quantum theory behind that. Yeah, the interpretation, I mentioned this earlier in quantum mechanics. I should say here that almost all approaches to quantum gravity preserve the linear structure and therefore the strict validity of the superposition principle, which means that at least in many, even if implicitly approaches, you use the average or a related interpretation. I mean, when I say average, I mean in contrast to, say, collapse models. David, in his pioneering paper, said it as follows: Everett's view of the world is a very natural one to adopt in the quantum theory of gravity, where one is accustomed to speak without embarrassment of the wave function of the universe. It is possible that Everett's view is not only natural, but essential. Actually, it was he, in 1967 and the years following, who made Everett's interpretation well known. Almost no one did know before. I mean, Everett, this was 57, and he was a student of John Wheeler, but he left science very early. He was a bit frustrated. He was sent by Wheeler to Bohr, and Bohr, I mean, did not treat him in such a way that Everett wanted to leave science. But David then, in the context of quantum cosmology, so the last thing, how much time do I have?
Oh, not anymore.
Huh?
You can finish soon.
Okay. Yeah. Then, so this is about primordial fluctuation. So one can, in this context, talk about a hierarchy of classicality. So, which I mean that this I have not shown. I say it in words. So in full quantum cosmology, if you have the coupling that comes from general relativity, the scale factor is the first thing to become classical because it entangles most with gravitons and the like. So if you have this, then this inflaton field is the next. And if you have then the background, so to speak, the decoherent background, the next thing are these primordial quantum fluctuations. And so according to inflationary models, so David said it in words in the morning, you have this, all the structure in the universe can be traced back to quantum fluctuations in the very early universe. This is of course a model, but inflation, even if not in detail, but in its qualitative features, is tested to some degree. We can at least base our assumption on it. So there are small perturbations of the metric and the inflaton field, and they can be described by a massless scalar field in a, here I only treat a flat Friedmann-Lemaitre universe. In this formalism, and this is also used by, not just by fundamental cosmologists, but also by people who are doing, say, structure formation. If you look into the book by Patrick Peter and Jean-Philippe Husson and others, of course you quantize metric and inflaton. So this is often overlooked, that if you do the perturbations, that people use also for the metric perturbations A's and A daggers and all that, like we do in our quantum mechanics classes. So you have here a formalism that makes use of a quantum gravitational field, and that leads to observations also. Of course, as I give here in the footnote, the gravitons, they have not been directly discovered. These are so-called tensor modes of perturbation theory. Some of you may remember 2014, there was a big hype of the BICEP 2 at the South Pole measurement, and they say they have discovered that. So they would have then maybe a window to the tensor modes, the gravitons of the very early universe. It later turned out that this was not true. I mean, they have some foreground, some dust in our galaxy. But if it were true, or had been true, then this, I would say, would have been really the first empirical test of quantum gravity, because in the formalism that was tested, these gravitons are treated really quantum and not classical. Now for the following, it's a bit shortcut. I don't want to bore you with too many calculations, of course. I use this variables y for the fluctuations. K is the wave number, or the absolute value of the wave number, which is the opposite of the wavelength. So the big advantage here is that you have small fluctuations, so they do not interact with each other. And this is why you can do all of these calculations on paper, not like later galaxy evolution with big computers. So these are small fluctuations that are independent. So you can treat them in a sense quantum mechanically by having each case separately. And this is the yk. The yk is defined as scale factor times the Fourier component of that scalar field phi, which can be the density fluctuation, scalar modes, also the tensor modes. There you in addition have these polarizations, but basically you can also treat it like that. And it has the properties y minus k star. So in the following, for simplicity, I just treat one real mode y. You have two, you have a real imaginary part, but I only have them. So, and because you have this background and you have this Born-Oppenheimer approximation, you can have a separate quantum mechanics, even a Schrödinger equation, and for each mode separately. And this is written down here, I, h bar, d psi, depending on y and t. The t is that semi-classical time that comes from the background, over t is h psi. Okay, the h comes from the Einstein-Hilbert action at the end. But this is standard textbook calculation. So you have here, for each k, this harmonic oscillator part, p squared plus k squared y squared. And you have this coupling to the expanding universe. So if there were no expanding universe, nothing would happen. I mean, you would have free fields in a flat space, and that's it. Yeah? But you have this 2a dot over a times y. P is the momentum conjugate to y. Now I've skipped always the index k because it's each k is separate. And people from quantum optics who know maybe nothing about cosmology, they immediately know that this term gives what is called a squeezing of a quantum state. No? That I will show what it is. So if you have an initial condition, we say it's a ground state, so the harmonic oscillator ground state, then we can solve, I mean, this is quadratic, and fortunately, so you can exactly non-perturbatively calculate a solution to psi. No? You could even give it to a quantum mechanics 1 student who knows not the cosmology but just the calculations. And what you get is, okay, these are explicit results, maybe you don't have to look at. Sorry for the diagram that you cannot really see it. I should have a more focused one. But The point of the squeezing is, I mean, the ground state in phase space, and we have here the phase space y and p, can be represented as a circle because it has equal uncertainties in y and in p, in x and p. And this squeezing means that you have you develop out of this circle a certain ellipse in a certain direction. This is the squeezing direction, and a certain size. So the squeezing is described by two parameters: the direction, which is an angle, and the size of the ellipse, which is given by this squeezing parameter r. And so one axis is e to the plus r, and the other axis is e to the minus r. And so you can show here then that this circle of the ground state gives an ellipse and rotates eventually to this horizontal axis, so that the squeezing is in y and not in p. No, quantum opticians, it's also their daily bread to deal with these things, and quantum optics books are full of results in the laboratory where you have this squeezing. You can generate this squeeze state, but as always, cosmology is a bit more extreme. So the squeezing that you can calculate for the modes that are also observed in the CMB, the cosmic microwave band, they have this squeezing of r more than 100. What does it mean? That the ellipse has axis e to the plus 120 and e to the minus. So it's a very thin ellipse, in fact. And this ellipse lies almost like it lies horizontally with this angle, so it's a squeezing in y, squeezing in position and not in momentum. And this you can calculate. And this is relevant for the quantum to classical transition. This is what is relevant here. So I put here these two results. So first, that if you treat these fluctuations isolated, so no environment, nothing, then for r to infinity, we get, and 120 in this context is already very large. I think the lab, maybe you can generate r's up to 5 or 6 or something like that. And 120, I mean, it's e to the, you must have this exponential, e to the minus 120. This is very, very small. You cannot generate this in the lab. But you can show that even if it's isolated, we have a semi-classical quantum state. If you calculate expectation values, they are, for practical reasons, indistinguishable from classical stochastic mean values. That's what Polarsky and Starobinsky demonstrated, and I joined them in 1998 because of the point that, okay, they are not isolated because we would assume they are coupled to other degrees of freedom, or maybe nonlinearities from, as we have learned in the morning, there could also be intrinsic nonlinearities. So you can have many environments, and in fact in literature you find many examples. And then one can show that the highly squeezed data are extremely sensitive to interactions, and that you actually can have the decoherence by following what is in the quantum optics books. In fact, and what you can really show then is also the preferred basis of classicality, because there was a dispute in the 90s. Some people claimed it's the particle number that is classical, but particle number is a mixture of p's and q's, right? If you have the particle number operator is A deca A, and so it mixes p's and q's. But what we showed there, and I think this is correct, is that it's the y, the position, because of that squeezing in position that gives this a classical basis, and not the particle position. And this has even relevance for the cosmic microwave background, because if it were not so, then you would not see these peaks in the CMB anisotropy spectrum. So this is for the more details, which are here a bit shortcut, but the time scale that comes out is, apart from some complicated numerical things, basically the time scale that is in inflation is the Hubble time of inflation, which is the order of 10 to the minus 34 seconds or whatever. So that h to the minus 1 gives also the time scale of inflation. Interestingly, there's an analogy to chaotic systems because this H corresponds to what is there, the Lyapunov parameter, making the classical appearance, the chaotic appearance, although this has nothing to do with chaos here because it's linearized, linear quantum mechanics, so there is no chaos. Yeah, okay, these are the details for the axis of the Wigner ellipse one gets. So the major axis stays around e to the r, but the minor axis does not go to e to the minus r, but has a certain minimal value, which can be given by this decoherence parameter, no, that is here in the density matrix here. So that's the parameter of the model. I mean, whatever environment you take, of course, you have a different parameter, and that psi is here a free parameter. Yeah. So we calculated the entropy, because also there we found different results in the literature, and if with that reduced density matrix you calculate it for Neumann entropy, you can see how the entropy develops here over S over, okay, chi is a measure of time, and what the main result here is that S, that this you can prove analytically, S in natural units is smaller than R, this squeezing parameter, and this is the half of the maximal entropy. Because if it were the point, if the classical basis were the particles, then you would get the maximal entropy you can show. But the maximal entropy, if that were really true, then you would smear out the structure in the CMB where you see the fluctuations. So you would not understand that you see this coherence of this fluctuations. So this is a point where, I mean, of course, ordinary cosmologists are not interested in this. So as we saw in the morning, now, of course, you have then at one point the classical stochastic fluctuations, and that's, I mean, what my astrophysics colleagues only want. And if I tell them about these things, they think, okay, decoherence and superpositions, that's maybe a bit outside. But it has here some relevance. No? If you believe in inflation, then you have to face, I mean, this quantum to classical. I mean, you cannot just put it under the carpet by words. Yeah, the last part, I mean, maybe, I'm not sure, I think I've already taken over the time. I have three, these are, maybe I don't want to be too technical, so I maybe more or less skip that. I just want to emphasize that one can apply, and this is also what we have done, the machinery of open quantum systems. You know? So master equations, then a Lindblad term, and all that. You don't have to know that here, but this is a certain standard formalism. You know? Yeah, I can try to. Yeah, I can die. So that's the first line, and so this is other work here. That we have here, and also with Lajos György, I did something that has nothing to do with quantum gravity, and so we investigate. The point is there are many models you can discuss for environments and the primordial fluctuations, and you find many in the literature. Some where you have an external field like coming from a string effective action, others from the nonlinearities of the same field, like a 5 to the 4 term, and so on. And in each of these examples, of course, you can make these calculations. What we did here in that calculation by, again, with Polarski and Starobinski, and Doma was a student of me at that time, was to discuss this at a general level of a master equation. So assuming that whatever interactions you discuss, you can describe them by a master equation that is of a Markovian, so local in time type. You know, that there may be exceptions to that, but the point is that many interactions lead to that. And for decoherence, you need to have at least one that makes you classical. You know, so that's what we did in that paper. And to make a long discussion short, I mean, we discussed more precisely now the decoherence time, and again find this, like before, which was more, I mean, more qualitative, this Hubble parameter, Hubble time, and okay, some logarithmic corrections, that maybe are not so relevant, and also discuss this for other periods. And so the outcome of this is that, yes, you can really discuss these primordial fluctuations with standard methods known from open system quantum theory. And so there is, it's a different field, it's cosmology, but if you give certain quantities and certain assumptions, you can use this machinery. So we have exploited standard things that were not done by us, but applied to that. And so you can then understand the original structure from quantum fluctuation. So that's a nice picture from the James Webb telescope. There you can look into the early universe and see primordial galaxies. And according to inflationary cosmology, these galaxies grew out of classical stochastic fluctuations that you can see in the cosmic microwave background. I forgot to include the CMB picture, but I think you had it, or yeah, you had it, yeah, fortunately. So out of these fluctuations that you see there, which are treated classically after decoherence, these galaxies grew. So that's the mechanism. So what I find fascinating here is really this unification of, say, fundamental questions in interpretation of quantum theory and quantum optics and galaxy formation. So the small and the large that comes together here. So that's the last slide. So then, so these reflections. So in principle, you could talk about each of these a separate talk or think about it. So, but what I emphasize here, the first is that I believe that according to what I've said, time and with it also probability, and we can discuss this maybe at the panel session or so in more detail, are emergent concepts from quantum gravity. So the full Wheeler-DeWitt equation or loop analog or string analog is timeless and has no Schrödinger equation, and also it's not clear that you need then probabilities at a timeless level. But when you have an emergent Schrödinger equation, you have, of course, the conserved inner product with it, which would give you an emergent probability, certainly. But this is something, of course, to reflect further. The hierarchy of classicality I have mentioned, so one can really make a diagram from the scale factor to this inflaton field to the primordial fluctuations, then to macroscopic quantities. The origin of irreversibility I have not touched here. So last year, I think in Geneva, I have talked about that, but that also is related, but would be a bit maybe too far for this afternoon. Still there are, you see papers appearing on this topic. For example, just I think before I came here, there was a paper on the archive by Chinese colleagues talking about the violation of Bell inequalities for the primordial fluctuations. So I have not read it in detail, of course, many technical details. So the question is, okay, you have decoherence for the fluctuation, so can you really measure quantum properties by observations? I would have said it's illusory to do that, because with these small numbers that you have where the interferences are suppressed, I do not see how even a future satellite can see that. But there are authors, and maybe I'm wrong, who discuss a possible violation of Bell inequalities in correlations of these fluctuations in the sky. That they exhibit or in short words, that the quantum nature is seen in spite of decoherence. I don't know whether really that's true, but I may be wrong. And a new field also that's, I see now more papers on quantum primordial black holes, because primordial black holes have now become one of the maybe serious candidates for non-baryonic dark matter. But we have not yet seen a primordial black hole. But yeah, or indirectly, indirectly seen, but at least it's not the consensus that primordial black holes have been seen. Also, it may well be true today. I agree with that. But they are also quantum at the beginning, and of course their classicality is also an issue. And so I leave it with these reflections, and thank you for your attention. continue.
And then you're quick to say, this is my time. Okay,
yeah, you are. I had to be quicker because of the chairman.
No, sorry. But I guess can you say more about what's the reason actually I should call that time?
Yeah, I think I can use that. There is some pencil or something. And I could just
formally you get something that looks like time.
Yeah, then I could just have a brief diagram, and then maybe it becomes clearer, or I can say it in words.
You have a pen, please?
I don't need the technical.
Okay, no, just a picture. The point is when you do that formalism, so then you have this e to the is. What you have then is, according to the Hamilton-Jacobi formalism, in the configuration space of the three geometries, you can have then hypersurface of constant S, this iconar, like for the geometric optics, and the light rays in optics, they run orthogonal to it. And here also this emergent trajectories, they are space-time, they run orthogonal to this S equals constant. And so I know that this is an emergent four-dimensional quantity that emerges only in that approximation, and I can parameterize it by, okay, I wrote down time. Of course, I should write down a so-called many-finger time to do justice to Einstein's theory, because these are not just light rays. You have a three-surface, and on each point of the surface, of course, you have an independent change because it's four-dimensional. But it's difficult.
The question is really like, okay, you can do that mathematically.
Yeah, you can do them, and you can maybe even draw this, say, not in 3+1, but maybe in 2+1 at least, as a projection. You can produce pictures.
My question would really be like, after that big conceptual leap you made, that this is time.
I don't say that this is the time with a definite article. This I would not dare to say. What I say is that you can introduce a parameter that has the property of what we call time. I mean, if you have then the Schrödinger equation, and you can also have for the S the Hamilton-Jacobi equation, and you get this term, this Hamilton-Jacobi equation in quantum cosmology, then is equivalent to the Friedmann-Lemaitre equation of cosmology if this thing is the same T as is used as the T in Friedmann universe, the Friedmann time. Yeah. So in this sense, I do. I mean, what is D time? I probably don't know, but it is D time parameter that is appropriate for classical cosmology. So I can build a bridge from quantum cosmology to classical cosmology by that. So I find the classical equations of Einstein as approximations and see if I do this identification, then this nabla S nabla is my D over D Friedmann time. In that sense, it's meant, not more and not less. I mean, it's up to the discussion maybe to whether we accept that. So, and of course, that's not enough, no? Because you have these superpositions, and then comes the problem with decoherence. Yes, certainly.
But so that you agree that decoherence will produce for you this density matrix, which at that point represents an improper mixture, and somehow you need some type of Decoherence approach to justify the conceptual jump to regard it as describing proper mixture of individual realizations, and also in the double universe is one of those individual realizations. My question is, in the Decoherence approach, one has this question of how do I select the basis,
right.
How do I select the manner in which I would regard the branching of the wave function as grids representing alternatives. What
of course the central question. We will come back to it also after the talk and the panel discussion. It's a central question, and this is certainly what was lacking in Everett's original paper, no? Because that was also the main criticism, that you can expand, of course, the wave function to whatever you like, and what is the classical basis. So this must come from somewhere else, and the concept of a pointer basis is, of course, something that in principle has to be calculated from the dynamics. Of course, you have to make inputs. I mean, you have to know what your Hamiltonian is, and you have to know what maybe your system is, your quantum fluctuations, and what are the other things that interact with it, and that you can consider environment. This somehow you must know why we can do that split already. I mean, why, for example, there are already localized systems like V in a non-local quantum world I don't address or I don't know. So this input, but then you can in principle calculate the pointer basis. So simple examples are that if say, what are the interaction terms, say in quantum mechanics, typically is in position, not in momentum. And if this interaction term dominates, then it's the position that is the pointer basis. But if also the kinetic term is relevant, for example, an oscillator, then it's the particle number, can be the particle number base. Yeah. So in principle you can calculate, and at least here for the primordial fluctuations we have calculated and come up with the result that it's the position. Position here means the amplitude of the field, that is the classical basis. So the claim, at least here, is, if this is all, of course, correctly understood, is that the pointer basis is derived, then you can derive the corresponding entropy and so on, which is different for different. Of course, in other situations, it may be difficult to know, or maybe not possible to calculate, but at least that's the, I would say, the ambition, no? To have inputs, Hamiltonian and degrees of freedom, and output which gives you the classical pointer basis. Or is this not a trend, or have I not understood properly your point? I guess you have this point, and this, I think, would complete the Everett picture. So I would say then, just to think that I mean, I don't know whether the Everett is correct, and I think I don't know about future developments, but I want to claim that this is a consistent picture at given present knowledge.
I mean, the friendly amendment I might make to that, because I think about it, is that it's not as if we did the decoherence calculation and derived these autonomous high-level equations, and then have an independent question to ask about what the third basis is. It's the existence of autonomous dynamical equations with respect to these degrees of freedom that make it true that those degrees of freedom constitute the third basis. You know, at least in the kind of Gelman-Hartle style way of thinking about decoherence, which I think is at least completely compatible with the way you're talking about it, then what it is for some basis to define branch structure is the existence of autonomous dynamic equations of exactly the kind that Claus has been deriving.
Yeah, I agree with that.
So would you think that's possible? Is it possible that we should add to the Everettian?
It's a statement of how emergence works in statistical mechanics in general. I mean, you can then ask a question as to what justifies the probability of the second conversation.
Right, next question from this. Or, yeah,
I'm sorry, I'm key.
okay. Yeah, okay.
there are of course other quantum black holes. I mean, Francesca has also discussed. I mean, that we, for example, that we are collapsing bodies so that you have a black hole and white hole thing. But they are not necessarily related to primordial fluctuations. Cosmology is more like general collapsing. I mean, I was here thinking about really the primordial fluctuations and the primordial black hole. And I would like to know the answer, but I cannot give it to you. But I hope I can give it to you.
Yeah, that's
and you
good.
can think about it.
Please, David.
I mean, this may just be a terminology thing. You said that if Bicep had the interpretation it originally had, that would have been the first test of quantum gravity. So I'm wondering why we wouldn't want to say that the predictions for the spectrum of the CME isn't a quantum gravity prediction.
Yeah, well, I say it, for example. But when I said that there are this time in the community who give the following argument, who say like Steve Giddings once objected it, and I called it quantum gravity effect, that it could, I mean, that you could also have the formalism with, say, a given classical metric, without really having to quantize a net decker. I mean, I know the formalism, these are called Sasaki variables of cosmic perturbation theory, and the metric and the perturbations are really on the same footing, but these other people say that the metric in a sense can also be understood as just relabeling classically the field amplitude, and then it's quantized. But my opinion is that we can already call this an observed effect of linear quantum gravity, because when you look at all of the textbooks and papers on cosmic perturbation theory where people discuss the spectrum, and there are many papers because this is our topic with the CME, then they use what we learn in quantum mechanics 1. I mean, you have this, they are oscillators because they are small, and the metric and metric fluctuations and the phi factor, they are combined with this E, which is the anostastic variable. And this variable then is subject to A's and A deckers and so on. So that's why I would think that this you can call. But I know from experience that other people have arguments that somehow you can understand it as a classical reparameterization, and then in a sense you have quantized the reparameterized inflaton field.
I mean, I suppose,
and not the metric only. With the tensor modes, you would have the metric only.
Yeah, and there's a degree of freedom issue as well, isn't there? I mean, you certainly see that obviously it'd be more exciting to see quantum gravitation degrees of freedom.
Yes, yeah.
But even see the sort of slave metrics and stuff. So.
No, you see that. Yeah, so in this discussion after my talk, it is definitely believed that if this tensor modes so are seen, if Bicep 2 and then this would really be a test. But with the other, that you have a mixture, and you can call it a classical reparameter. Yeah, maybe it's a terminology also, but in my opinion, otherwise I would have different formulas. If I say the metric is always classical, why should I combine it then in this Mukhanov-Sasaki variable? And it's equal footing. So if the V is the delta, well, there are some other factor d phi, and then you have the delta metric together, and this is what you find in papers on cosmology. squeezing is a quantum property of quantized harmonic oscillators, and the point is that these, it's not chaotic, I mean it's just linear quantum mechanics, there's nothing chaotic, but these squeezed systems, they are very sensitive to, say, perturbations, right? So this, the isolated squeezed state would just be this small ellipse rotating around. And if we have an interaction to a system that measures or interacts with it at a position, then you get this freezing here, and that you have a classical appearance of the position. And the time scale that happens is here this h to the minus 1, which just from the pure formula, not from the context, appears at places where for a harmonic system the Lyapunov covariance would appear. Yeah? And this is why I made that remark. So it's only a remark because it's from the formula, it's nice to see similar formula, but the interpretation is very different. A linear quantum system versus a nonlinear classical chaotic system.
Right, we have time for last question.
So thank you. I was just wondering, because you mentioned like that quantum gravity has to be applied like to the universe as a whole. You mentioned also like the process of decoherence when you talked about this. And since this morning we were talking a little bit like the possibility of implementing decoherence within a sort of relational interpretation. But I don't know, like in these relational approaches, like you never treat the universe as a whole, right? So
in the relational approaches, you never did. Well, I mean, here I treat the universe as a whole, always quantum, and assume that fundamentally all the degrees are quantum, and that classical behavior is an emergent thing. So I don't subscribe to hybrid theories, you know, where you have a world that consists of exactly classical parts and exactly quantum parts. It is of course an assumption, but I think there are reasons for that. And so, what's going on?
no, I was just wondering because like if you want to, I don't know, can this work also in a relation, like when you?
Yeah, but relational can mean different things. I think I can accommodate relational things here also, because in a sense you have this relational, I mean, when you derive this time-dependent Schrödinger equation as an approximation, it's also based on a relational approach between what is here called the background degrees of freedom and the environmental or perturbation degrees of freedom. So of course there comparisons or pictures do not always work, but it's like when reading a book, say a book is also timeless, everything is there, but when you read it, then you have the impression that time passes. And this is comes from the relation, say, between you as the reader and the letters. Or then you have a partiture of music, you know, it is also there, but if you play it, then also time seems to come. It's not from the partiture itself, but from the relation of the one who played, say, piano or whatever. In this sense, relational can also be there, but I think you mean relational in a different sense. No?
No. Yeah, I was just wondering. Yeah.
Yeah, but I should also, maybe I should have emphasized this more, because it was also on your transparency that here in this approach, you first have this one Oppenheimer approximation and this recovery of emergent time, and you discuss then the decoherence then, you know, after that. I mean, at a full level of quantum gravity, where everything is quantum and timeless, I think there is not yet decoherence and also no measurement problem. I think these problems, and